Hello, welcome to Noise Control and its Management. Today is the third day of the 11th week of this course. This is the second last week of this course, and over last several weeks we have been exploring different ways to control noise and reduce the overall level of noise both indoors as well as outdoors. So, we have been discussing several ways to reduce noise, and one way we have focused over last couple of weeks is to reduce noise by putting enclosures. Now, these enclosures essentially are cover the surface the source of the noise from all the sides, but in a lot of applications it may not necessarily be feasible to enclose the overall source of the noise from all the sides. In other cases it may be feasible, but it may be very expensive. So, today and also remaining part of this week we will discuss how to reduce noise by having barriers. So, essentially barriers are vertical walls between the noise and the place where we are interested in reducing the overall noise level, and let us see how these barriers work out and how can we design these barriers to meet our specific applications. So, what we are going to discuss today are barriers. Now, you can have barriers either outside the room, or you can have barriers inside. If you have barriers outside, then you would not expect a lot of reflections to be occurring. So, here the job of the barrier is to reduce direct sound which is coming from the source. But when you have barrier on the inside, the barrier does two things. It not only stops, its job is not only to stop the direct sound which is coming, but it is also there to somehow also reduce the reflected sound which comes to the point of listening. Now, in either cases, both these situations, barriers work well if both these conditions are present. First condition is when direct noise dominates. If most of the noise is not direct, but coming from reflections, then if you put a barrier between the source and the listening position, it will not help much, because the noise has other paths to reach the point of listening. So, when there is most of the noise is direct, then barriers work well. The second thing is that barriers work well, and both these conditions should be present. So, first is when direct noise dominates, and the second one is when noise has large high frequency content. Barriers do a very poor job in terms of stopping the propagation, spread of noise, especially if most of the noise is at low frequencies. But if it is high frequencies, they do a very good job. So, we should understand these two things before we start designing barriers. So, if we think that our situation is such that we have a lot of low frequency noise, then probably we should not worry too much about barriers as a way to reduce the overall noise level. And also, if we think that a lot of noise is not because of direct transmission, but it is coming because of reflections, because of reverberations, then again we should not worry too much about having barriers to solve the noise problem. What we will discuss today and probably tomorrow also is barriers which are located outdoor. But before that, I wanted to again point out 2 or 3 things as to how barriers prevent spread of noise. So, suppose you have a source and this is we have a listener. What happens? So, noise can directly reach there. So, this is a direct noise. Once I put a barrier, this is a barrier, then this transmission, direct transmission gets stopped, then noise reaches the listener in two ways. One is it goes here and then from here it diffracts and it comes like this. What is diffraction? It is the bending of waves as they travel around sharp corners. So, this we have seen in case of light also, light diffracts, it bends around corners. So, when there is a barrier, sound waves diffract and then they reach. So, this is one path through which they reach the listener. Okay. And then of course, a lot of noise will be going out in air, and if there are no reflecting surfaces, it will never come back. So, this is path 1, it goes there by diffraction. The second thing is the sound comes here and some of it gets absorbed and then it gets transmitted, and then part of that sound gets transmitted, part of that sound gets transmitted. So, what do barriers do typically to sound? They reflect the noise, they diffract the noise, they transmit noise, okay, and they do not transmit all of the noise. So, depending on how good a barrier is, it will transmit only so much amount of noise, and then finally, they absorb noise. But the absorptive effect of barriers on noise is not significant, particularly if we are thinking of outdoor applications. It is not a whole lot. So, when we are worried about barriers on outdoor applications, what we are particularly concerned are about these three factors. How much of a sound is getting reflected, how much of it is getting transmitted, because absorption is not much. So, whatever is coming in either gets reflected or it gets transmitted. And then of course, if the sound reaches end of the barrier, it gets diffracted and some of that sound reaches the listener. So, these are the three things particularly important for outdoor applications. So, with that introduction, let us look at barriers for outdoor applications. And what I will do is, so first let us look at a picture. So, this is a barrier, okay, and let us say this is a sound source, and I have a listener here. And let us say this distance, with respect to ground is d, in the horizontal direction is d, and this distance from the source to the top of the barrier we will call that A, and from the top of the barrier to the location of the listener we call that B. So, we are all these dimensions are in meters, all these dimensions are in meters, and let us say that the absorptive coefficient, transmission coefficient of this barrier is 80. And how do we find what is the transmission coefficient? We find 80 either through FEA, or if we are purchasing it from a vendor, then we should ask the vendor what that number is. So, either we get it from FEA if we do it ourselves, or if we are purchasing it, then the vendor should give us the value of 80. If not 80, then we should know the transmission loss. From transmission loss we can compute what is this parameter. So, if this is the situation, and let us say this sound source is producing W watts of energy. So, the sound power level is LW, then the value of sound pressure level at the listener location, I will write that directly, and that equals LW plus directivity index. And what is directivity index? It is 10 log of directivity factor minus 20 log of A plus B minus 10 log of 10. So, all these are to base 10, 10 log of 1 over AB plus AT plus 10.9. So, this is again in decibels, and I will explain what is AB. So, this term, it accounts for how much sound is getting transmitted through the barrier. Okay. AT. If AT is large, then LP will be large and vice versa. So, we want AT should be as less as possible. This term actually, okay. So, this term is related to the fact that how much of the sound is getting diffracted. So, how much of the sound gets bent and it actually reaches the listener. So, it captures the diffraction effect. Captures the diffraction effect. And how do we calculate it? I will explain it to you. So, once again, if AB is large, then it is not a good thing. We want AB to be as small as possible. And of course, A plus B tell us how far the listening point is relative to the top of the barrier. So, if A is large and B is large, then it is a good thing for us. So, this is the role of distance. So, if I have to reduce my LP, I should increase A, I should increase B, I should reduce AB, and I should reduce AT as much as possible. Now, AB is called barrier coefficient. It's called barrier coefficient, and you can actually calculate it in this way. So, it is tan hyperbolic square of it of 2 pi n, the entire thing you have to take a square root, divided by 2 pi square n, when n is less than 12.7, and n is called Fresnel's number. So, if you do some studies on diffraction, you will see this term, Fresnel number. Okay. And this is equal to 0.004 for n more than 12.7. And what is n? And n equals 2 over lambda. So, again, so now here the wavelength comes into picture, 2 over lambda times A plus B minus D. Or if you want to express lambda in terms of frequency, then it is 2f over C times A plus B minus D. So, for each frequency or bandwidth of interest, you calculate n, that will help you calculate AB. That AB you put in this relation, and of course, if you know AT, then you can calculate LP. Okay. I wanted to show you the how does AB change with respect to N. So, I have a graph for that. So, this is the graph for barrier coefficient. So, what does it show? That as N becomes small, the barrier coefficient, so this is AB, as N becomes small, as N goes down, AB goes up. The maximum value possible for AB is 1, okay, is 1. But as it becomes okay, and after 12.7 it does not change much. So, it remains at around 0.004. So, that is why we have given two conditions, if it is more than 12.7 it is 0.004 and so forth like that. And as N goes up, AB goes down. What does this mean? If AB is going down, remember what did we say about, so this is my source and this is a listening position. So, if AB goes up, then more sound gets diffracted, right. If AB goes up, then more sound bends around and it reaches the listener. So, the barrier becomes less and less effective. Okay. So, as N is becoming less, AB is going up, AB is becoming more and barrier becomes less effective due to diffraction effects. And what does, and how does AB become, how does N become less? Now, we have shown or we have written that N equals twice of frequency divided by C times A plus B minus D. So, as I reduce my frequency, N becomes less and AB becomes more. Okay. So, more diffraction happens at low frequencies. So, if you have very low frequencies, probably the barrier will not be effective at all, it will be just transparent to noise, all the sound will just go there and reach there. Okay. So, this is important to understand, but if the frequency is high, then this becomes, AB becomes small and we get the benefits out of it. So, what we will do is, so I wanted to give you this understanding of the physical understanding of what is implied by AB. Okay, so, the other thing is, look at this term A plus B minus D. So, this is the other term. A plus B minus D means the difference between the path if the sound goes like this or if the sound goes straight away, right. As this wall becomes higher, so you can have case 1, let us say these are the two positions, then the sound has to do this, that is not a so much of difficult thing to do. But as the wall becomes taller, the sound has to take a very sharp turn, and as it keeps on becoming taller and taller, it has to take more and more sharp turn, okay. And it becomes, things become more difficult for the sound to do that. So, and how do we know whether it is going to take a sharper turn? It will depend on this parameter A plus B minus D. If A plus B minus D is equal to 0, then the sound will just go straight away, but as A plus D goes up, the sound is taking a more sharp turn. So, this is another thing. Okay. So, this is the role of geometry in this relation, not only role of geometry, I mean role of geometry. So, it should be geometry on diffraction. Okay. So, the point is that we should make as high a wall as possible, for this barrier to be efficient. The last thing I wanted to talk about is traffic noise in context of barriers. You may have seen, especially on bridges or some highways, that sometimes next to the highways, or if a highway is going through a very populated area, nowadays at least in our country, people are putting barriers across the roads. So, you have a road and they put some barriers. Especially if there is high population density in this area. And the purpose of those barriers is all the noise which is coming out from the cars, continuous stream of cars. These barriers are there to reduce the noise propagation to these populated areas. So, this is the problem of traffic noise. Okay. Now, in case of traffic noise, we do not have a point source, because till so far the relation which we discussed was for a point source, but in traffic noise it is a line source. Okay. It is a line source. And if we are creating barriers to stop the noise from a line source, then with barrier and without barrier. So, if with barrier, let us say, without barrier, let us say the sound pressure level is LP, and with barrier, let us say sound pressure level is LBP with barrier, and this is without barrier. Then in both these cases, so then we would expect that LBP should be less than LP. So, what is the improvement in sound level because of barriers? It is delta LP, which is equal to LP minus LP in presence of barriers, and that equals 15 log of 10 A plus B by D minus 10 log of 10 1 over A B 3/4 plus AT. Okay. So, this relation is good for traffic noise. This relation is good for traffic noise, because noise is not just coming from a simple point, it is coming from several points which are there in a line. So, that is why it is a line source. This relation is for noise coming from a single point. Okay. So, we cannot use this particular relation for traffic noise, and because barriers are used very often for traffic, so this is the relation you should understand. So, that concludes our discussion on barriers. Tomorrow we will do actually an example of barrier noise and how we can use barriers to reduce the overall noise level. So, with that we conclude for today, and I look forward to seeing all of you tomorrow. Bye.